apply the technique of factor analysis, what you learn in class. So the rationale behind the project is just to test your knowledge or understanding of what we've already learned in class. But what I'm going to do after assigning everybody to group, I think I'm gonna mention the guideline again, so that that will guide you on what to do. But now be looking for data. Okay, then you frame a topic around the data. Of course, you're gonna do analysis of the data. Okay, using the technique. Okay, that whatever technique that fall in the area. Does that make sense? Okay. Once again, I want to welcome you to uh, statistical machine learning. Of course, on Monday, we started portfolio theory with covariance analysis. Let me tell you this, with analysis of covariance, of course, that can actually, that is applicable in most of the field, depending on what your intention is. Okay, so I introduce you to portfolio theory, how covariance analysis can be used. We talk about, uh, having different assets, how we can advise investors to spread the weight across variety of assets. We encourage them to diversify, and we don't want a situation whereby the assets will correlate. When asset correlate, uh it has a damaging effect on the risk. So what I want to walk you through today is how do we set up efficient uh, portfolio. Efficient portfolio is the one that have excellent diversification. And what are the factors, that can, translate into excellent diversification. And I'm also going to talk about how the use of constraint optimization technique is actually going to be used here to figure out the parameters, because the parameter in the model is actually going to be the weight. Okay, the weight is the amount, because investors really want to know what is the optimal amount of money that I need to commit to asset A. What is the optimal amount of money that I need to commit to asset B? We don't just you don't just spend money anyhow. Investors want to be statistically guided, and of course, with a quadratic optimization, with a Markowitz portfolio, of course, that is the way out. Okay, so once again, welcome to this. So I walked you through the portfolio theory yesterday, and of course today is how do we actually put in place efficient frontier. Efficient frontier is a portfolio that can minimize the risk. We always want to, there's a lot of risk in this life. Uh, we live in a stochastic environment, whether in finance, whether medical environment, whether physical environment, whether psychological environment, they are all found to be probabilistic. And of course, we need to be able to take a decision, a valid decision, under uncertainty. And how are we going to do that? Of course, you know, uh, it means we have to be probabilistic inclined, okay, and which is what I want to walk you through today. How do we actually construct efficient frontier? Okay, I've introduced you to this. I got different assets, PA assets. You know what I know, the billionaires that I know, they are not satisfied with one investment. Okay, they diversify, and you know what? Uh, the reason why they diversify is because if a particular asset perform poorly, of course, they're actually going to be compensated with the other assets, but provided they don't correlate. The moment assets move together, if one asset is in trouble, of course, the other also going to be in trouble. And that is why today I'm actually going to show you the effect of correlation on building efficient portfolio. Okay, so I walk you through this the other time. For a particular asset, I'm actually going to commit certain amount of money for the asset that I'm actually going to call WI. So if I really want to know the return from that particular, if I want to know the value of that particular portfolio associated with asset high, of course, I just need to multiply WI, by that. And of course, I think I walk you through this the other time. The bottom line is that the return, the total expected return that I'm expecting, what they are trying to tell us here is a weighted average of individual return from each asset. That is what this guy is trying to tell us. Okay, when you have an asset, you're expecting return from each asset. So if I want to talk about my total return from all assets, of course, it's a weighted one. Okay, that's exactly what I'm trying to say. I think I mentioned that. And of course, for a single period, because when you talk about portfolio, we could talk about for single period, we could have for multiple period. Okay, if I want to talk about for single period, okay, the return, okay, of the portfolio over the period is going to be this guy. Okay, it's actually going to be that guy. The WI is the weight. Okay, it's like the amount of money or the percentage of money or the proportion amount that you put into different investment. Okay, if you take a look at that. Now, let me tell you this. If the return from each asset is a random variable, we also expect the total return, okay, in the entire portfolio to also be a random variable. Or why is it that? Well, we borrowed the idea from statistical theory, okay? There's something, if I have a random variable S and Y is a function of a random variable S, then a function of a random variable is also a random variable. That's what I mean. So if ROI is actually a random variable, then R, which is the total return, the return, in the portfolio, also going to be a random variable. So, what are we looking for? We actually want to get the average return because in a stochastic environment, okay, in a probability space, we normally want to talk about average, why average? Because returns varies. Return is a random variable, and of course, we want to find that our average of that. Yes, well, the average of return is what we call expectation of R. That's a expected return, and of course, and that is actually going to be a weighted a weighted average of individual return from individual assets. You can see here expected value of R equal to a linear combination of the expected value of return from each investment. Okay, now how do we measure the risk of the portfolio? Okay, if I want to measure the risk of the portfolio, then I need the variance of the portfolio, the variance of R. Okay, and of course, the variance of R in matrix form is this guy. You take a look at this guy. It means I have a weight. A weight is a matrix. I can find the transpose, and what you have in the middle is the covariance matrix. Okay, so this is the variance, okay, of the portfolio value. Okay, if I want to write that in a maybe in a scalar form, okay, I'm actually going to write it this way, which is a summation of Wi, Wj. I'm actually going to have covariance that. Okay, now what this guy is trying to tell me, Wi greater or equal to zero, okay, that's a restriction that at least it said that you don't spend on a particular asset or you spend more than zero. We don't want a negative, okay? But I'm still going to tell you situation where W can be negative. That is what we call in short selling, okay? I'm still coming back to that. But right now, okay, we're having that. And of course, the summation WI equal to 1 because equal to 1 means you spend the total amount of money, the whole money on all of that, 100%. Okay, that's what it means. Okay, now we take a look at that now, uh, we actually what are the way to you know to develop efficient frontier, okay, 1952, Markowitz, okay, developed a theory, to for us to be able to have an efficient frontier. An efficient frontier is the one that can guarantee a reduction in the risk. We always want to reduce our risk. Okay. So now, and this is the rule of thumb. Okay. So the equation that I'm having here is trying to say, uh, after applying Markowitz optimization, the variance of the risk will actually be smaller than the variance of individual risk associated with the assets. Okay. So let's take a look at that. Now, I need you to pay attention. What I want to do right now, I actually want to show you the way my code, how it's set up, so what to minimize. Let me tell you the intention of my code. Intention of my code is actually the intention of investor. Every investor actually want to minimize their risk. Okay, they want to minimize their risk given a certain value of expected return. Okay, which is the same thing as they want to maximize their expected return or giving a certain level of risk. Okay, so because of that, because they want to minimize risk, if I want to minimize risk, I'm actually going to minimize the variance of of the portfolio. You remember I said the other time, this guy is a variance of the portfolio. Let me take you back in matrix form. I think I said that. Take a look at that. Sigma squared. The variance of the portfolio value is that guy in matrix form. And that is what every investor actually want to minimize. Okay. And because of that, we actually going to have a minimization, objective. We want to minimize that. But if you want to minimize your risk, okay, then it means minimizing your risks, then you have a certain expected return. That is, giving this value of expected return, I want to minimize risk. Okay, then this is going to be the constraint. Oh my God. If you take a look at what I have here, you know what that guy is telling you? That guy is the expected return. Given that you know the value of expected return, I want to minimize my risk. That's what that guy is trying to talk about. Don't forget, the expected return is actually a weighted average, the weighted average of, from, individual return. And the further constraint is that I don't want short selling. I actually want the weight, the amount that I'm actually going to, commit to each investment to be greater or equal to zero. And of course, I want to spend the whole money. Okay. The sum of the weight has to be equal to one. Okay. But let me tell you this, optimizing this guy, this can never be done using it's not a closed form. We have to go by way of iterative procedure. Okay, algorithm, we actually be involved. Okay, but you know what? We have the algorithm to use in R. I mean, we have a package that will help us with this optimization in R. We call the package CVX. If I load that package, then I will be able, to optimize my objective function. Okay, I'll be able to optimize my objective function. Let me tell you this. This objective function can be in two forms. Please pay attention. This objective function can be in two forms. This is the first form. You know what this guy is trying to tell me? I already have a given expected return. How can I minimize the risk? Then there's going to be another one that will say, okay, uh, given a particular level of risk, how can I maximize expected return? Okay, so that's another version, but the version that I'm actually considering right now is minimizing risk. Okay, minimizing risk or giving expected return. Okay, so now that is what I mean. Here I said in the interpretation, I said among all portfolios, there's going to be so many portfolio because we're actually going to have possibility of portfolios. Okay. Now, if I derive portfolio given a particular return, okay, the one I'm actually going to choose among them is the one with the smallest risk. That's exactly what we mean here. Okay. Uh, Go ahead.
It's like WT sigma W, like couldn't you just like take the like eigenvalues of like and eigenvectors of sigma and then just take like the lowest eigenvalue and then wouldn't that minimize that?
Okay, that's a very good. You actually want to see whether taking the eigenvalue. We have different kind of approach that can be used. That's also going to be one of the techniques, that you can use to minimize days. But the bottom line is we don't want to do anything that will be computationally intensive. We actually want to hide under a software. Okay, and that was why I said you may not even be able to understand what is going behind the scene. The CV, when I load a package, CVS, that will actually do the job. So there's so many ways we can achieve that. Okay, but I don't want to go more theoretical. What I want to do, like if you are doing this area in projects, okay, the moment you load a package, you actually just going to see results. Does that make sense? Okay, now I actually moving. Hmm, this is another one. I said we actually having the objective function in two form. The first one that I show you is minimizing the risk given a particular expected return. But the one I want to show you right now is maximizing, okay, maximizing the expected return. Okay, you want to maximize expected return given certain level of risk. Does that make sense? So that one is going to be maximize. Okay. This is like going to be the expected return minus this is the variance aspect, and of course the gamma here is actually going to be the parameter. Okay, where I can try to look at, I can vary the values of gamma. Okay, I say gamma is our conservativeness, okay, for the investment. Okay, a large value of gamma has implication, a smaller value has implication. So a large value of gamma indicates that we actually want to tolerate smaller risk. There are some investors, they don't like it, like they don't want to tolerate large risk, okay, because the money they want to, maybe they borrow the money from bank, they don't want to throw the money away. Okay, they can. So here, when I vary, but what is a reasonable values of gamma that is going to work? Okay, we can take the gamma between 0 and infinity. Okay, so take a look at that. Okay, so what I show you the other time is a quadratic optimization. What make it quadratic? Because of this guy. That's quadratic in nature. Okay, so we call that a quadratic optimization problem. Okay. And let me tell you this. Uh, we need to introduce a further constraint because we don't want the weight to have let me just say unpleasant behavior. Okay. Of course, in optimization, we normally introduce a Lagrange multiplier. You remember when I was walking you through Gaussian Mitchell model. Okay. Now we want to show you what is behind the scene. Okay, what is a function? This is the function. This guy is the risk. This guy is like the return. Okay, now uh what I want to optimize. Okay, optimizing, I'm going to differentiate. This is the first derivative. The first derivative, what am I doing the derivative with respect to? This is respect to W. Want to figure out the optimal values of weight. The investor want to figure out the what is the optimal amount of money I'm actually going to spend on each investment, and that's actually the W here. Okay, And of course, we believe a necessary condition, that the W star is going to be a maximizer or minimizer. When I plug that back into the derivative, it should give me zero. Of course, we all know this, as a fundamental belief in optimization. Okay, but you know what? The f of W here, okay, is when I was doing the optimization process, I did not consider Lagrange multiplier. If I don't do that, there's possibility the weight may have erratic behavior. Okay, it may be outside 0, 1. Okay, so because of that, we're actually going to add, can you see that lambda, the Lagrange multiplier? And it means the number of parameter has increased from 1 to 2. Instead of me to only focus on weight, I'm also going to focus on the Lagrange parameter as well. That's why you see W star and the lambda star. I want to figure out the optimal value for the weight. I also want to figure out the optimal value for the lambda. The lambda here is a parameter of the Lagrange multiplier. Okay, I want us to have a specific example now. Consider a portfolio with n assets whose single period arithmetic return is this. Let me tell you this. R1 is a return from investment, X1. R2, return. Every investment should have a return, okay? And that's what you're saying here. That's a vector, right? Now, if I actually want to find the return of the portfolio, don't forget, it's actually going to be a weighted average of the return from individual assets. So what you're saying here, okay, is the same thing as, oh, W1 multiplied by the return, multiplied by R1 plus W2 multiplied by R2, and so on like that. Does that make sense? Okay, sum of the weights has to be equal to 1. Of course, I told you what W1 represent. The W1, actually, the percentage of the total amount that you spend on a particular asset. Okay, and of course, if you take a look at this guy, this is a return of the portfolio in a scalar form. Can I also have a way to write that in a matrix form? This is in matrix form. Please pay attention. This is in matrix form. Don't forget, R here, the R here, it's actually going to be this guy, R1 out to RN. Take a look at that. Okay, so I think I just show you the return in a scalar form and the return in a matrix form. Okay, and let me tell you this. I said something here. I said the relationship allow us to compute the mean and the variance of the portfolio return if we know the mean and the covariances of individual returns. Let me tell you this. From financial data, okay, uh, you can find the mean of return, and at the same time, you can also find the covariance. Of course, you know how we obtain the covariance, the sample covariance, the covariance that you obtain from the data frame. Of course, you are able to do that, and with that, that's enough for me to, of course, to start optimizing the quadratic, function. Now, take a look at this. If R is a vector and that gives us return from each investment, then we're actually going to have a mean. A mean is also going to be a vector. This is like the mean for asset one, the mean from asset two, and so on, like that. Okay. Now, and the moment the mean vector exists, the covariance also exists. The covariance, we measure how the assets move together or how they move apart. Okay, now this is the mean of the portfolio now. This is the mean of the portfolio in a scalar form. This is the mean of this is the mean of the portfolio in a matrix form. I'm going to say that again. This is the mean of the portfolio in a scalar form. This is the mean of the portfolio in a matrix form. And if I want to find the variance of the portfolio, this is the formula. Okay, if you take a look at equation 2 now, the variance of the portfolio will enable us to measure the risk associated with the portfolio. Now, this is the variance of the portfolio in a scalar form. This is the variance of the portfolio in a matrix form. Okay, you know what have I given you? I've already given you the mean and the variance, the mean of the portfolio value in a scalar form and in matrix form. I also give you the variance of the portfolio also in a scalar form and in a matrix form. Now, we want to talk about diversification now. Okay, now let me tell you this. As noted by Markowitz, if you want to minimize your risk, then be ready to diversify. Okay, diversification will translate into risk reduction, according to which means what is the general rule? The variance of a portfolio can be reduced by adding in more risky assets. When you add more risky asset, okay, you are diversifying. Okay, and of course, I'm actually going to walk us through this. Please pay attention. Okay, I want to consider three situations. I want to start with this example. Pay attention. Suppose there are n assets returns that are uncorrelated. If they are uncorrelated, you know what is going to exist? It's only the variance. Variance of which will exist. The covariance is 0. Okay. Now, with equal variance, there's possibility. Okay, asset could have equal variance, and the return of portfolio weights are all said to be 1 over n. If they are all said to be 1, if the weight, okay, if the weight is said to be 1 over n, okay, then the variance of the portfolio will be sigma square over n. Why sigma square over n? Because for each portfolio, okay, for each portfolio, you're actually going to have constant variance, according to what it said, equal variance. Okay, there's equal variance, there's equal weight. If there's equal variance and equal weight, of course, the variance of the portfolio is going to be this. And let me tell you this. Oh my God. This is more or less synonymous with statistical theory that talk about average. The variance of S is sigma squared. The variance of X bar is sigma squared over N. Okay. But you know what? I want to show you that when N tends to infinity, you know what I mean? N tends to infinity. When this guy tends to infinity, okay, when that guy tends to infinity, the variance will tend to 0. If you want to go by limit theorem, okay, this guy is going to tend to 0. You know what that means? That is the reason if investor that actually invest equally to assets, invest equally to asset, and where individual assets are the same risk, if the investor want to drastically reduce the variance to 0, then it should consider a sufficient large amount of assets. That's what it's saying. So many issue where we're trying to say put that in so many assets. Asset tends to infinity. Number of assets tends to infinity. It means you got a lot of assets. That's what it means. Okay, eventually we expect the variance to converge to 0. Now I want to go into example 2. In example 1, we consider two different assets. We consider an asset, and we assume uh, equal weight and equal variance. But in example 2, we actually believe that there exists a covariance. Let's take a look at that. If covariance exists, okay, then the variance of the portfolio is actually going to be this. Please pay attention. The variance of the portfolio is going to be that. The other time, okay, when they are uncorrelated, it was sigma square over n. But now that they correlate because the moment the covariance is not zero, the correlation exists. Okay, now I'm actually going to have this, but in this situation, what can we do? If I want to drastically reduce, uh, you know, the variance of the portfolio, I'm going to set that to infinity. I'm going to set that to infinity. Okay, when n tends to infinity, okay, the variance of the portfolio will not tend to zero. The variance of the portfolio will tend to correlation sigma squared. That's what I'm saying here. Okay, and that was why I said adding more assets reduces the variance of the portfolio return, but up to a certain point, not zero, because they are what? They correlate. Okay, that's actually going to tell you the effect of correlation on that. Okay, I want to go into another example. Please pay attention. Example number 3. Lastly, suppose we have two assets, okay, and we are sigma 1 and sigma 2 equal to 1. They have the same standard deviation, and of course, correlation exists. Because they are two assets, weight is going to be W, 1 minus, the other one is going to have 1 minus W. The sum of W has to be equal to 1. Okay, now I need you to pay attention. In that regard, the variance is going to be this guy. Okay, the mean, I'm actually going to show you something. Okay, P equal W. Okay, if you have W, okay, maybe W on this asset, then plus the other one is going to be 1 minus W. Okay, it's going to be a mixture, then multiplied by the second asset. You get that's what we mean. So here, the variance of the portfolio will involve that. But let me tell you this situation where they are not related, situation where they are not related, this guy is going to be off, because this guy rho will be 0. That rho is a correlation. When correlation exists, the covariance exists. That's what it means. Okay, now if I now from here I take my W to be half, the meaning of half means I want to spend 50% on this investment, on this asset. I'm also going to spend 50% on the other one. That's half. When W equal to half, this guy, if you plug in half, where you see W here, please pay attention. I'm seeing a lot of final exam here. If I plug in half here, okay, this guy, the variance of the portfolio will become that. The variance of the portfolio here is in terms of correlation. Okay, when I plug in that, okay, but what if in a situation where my W equal to 1? You know the meaning? If W equal to 1, W equal to 1 means if I have two assets, I spend 100% on one asset and I spend 0 on the other. Okay, how would the variance going to be? It's going to be this. The variance is going to be 1. Then the standard deviation is going to be 1. If you try to plug in W to be 1 into this. And that was why, and then we get a strictly higher variance. Okay, don't do that. When we're going to tell the investor, don't do that. Don't put all your money in one asset. It's dangerous. You are not diversifying when you do that. Diversification reduces the risk. When you do that, you are increasing your risk. Okay, so that's exactly what we mean. Okay, I'm moving. Go ahead.
This part P there or rho and W. So that's variance, right?
Yeah, the sigma square is the variance of the portfolio.
So what is just is sigma not just standard deviation?
Yeah, so this one, I can use variance, I can use standard deviation, but why is it that we trust standard deviation to the variance? Because the variance is not in the same unit as the mean. But if I want to have a measure that is in the same units as the mean, then I will find the square root of the variance. Because the unit of the standard deviation and the unit of the mean, they are the same. But the unit of the variance is a square unit. The mean is not a square unit. Does that make sense?
Yes.
Okay. That's a very good question. Very good indeed. You know, when I was in college, I normally ask a question of why that, why.
Of course, it's not going to make a difference here. So now, actually going to move. Let's now talk about having. Let's talk about having. I want to go into. So now, when you look at all the examples that I've demonstrated, it's actually show that diversification reduce risk. Okay. I want to consider another example. Now I said something here. Before we discuss how to do this in Markowitz model, because we're still going to do this in the next class, which is the general situation. Let's consider two examples. Example one, a single risky asset and a free risk asset. At times, I can have two assets. One is risky, one is risk-free. Okay, I want to derive the variance. Then I'm also going to consider an example where the two assets are risky. Please pay attention.